Hello, everyone, and welcome to another webinar from Optiwave. Today's webinar would be on revolutionizing OptiSystem 23 software for UAV, LiDAR, quantum communication, and machine learning applications. My name is Ahmad Atiyah, and my collaborator is Dr. Abdullah Karar. He used to work with Optiwave and in development of some of these components in this release. He currently with Abdullah As-Salim University in Kuwait. Today webinar, we will give you an overview of Optiwave. Then we show you the product line, then discuss the new components added up into the new release of 23.0, and then discuss the improvements, demonstrate the new components. Then we open up to question and answer. Okay, so Optiwave is established in 1994, so it's over 31 years old. We are located in Ottawa, Ontario, in Canada. We do software development, so we design software for users to design, simulate, and optimize their links, component devices, and networks in optical communication. The software will allow the users to shorten their product line to the market. It improves the product quality as well as improving the cost effectiveness and enhancing the productivity. The product line of Optiwave is categorized into three categories. Is the system level, which we offer two software packages, is OptiSystem and OptiSpice. OptiSpice is an optoelectronics software which you would design your optical and electronic circuits in the same layout and do the simulation. So you can have the laser drivers, for example, electronics-wise, and add up to the components. Same thing for other components. The component level software, it includes many packages. It's related to mode solvers. So we have the finite difference time domain. We have the mode solvers. We have a new product, which is OptiOmega. This uses the GPU and it's solving the equations much faster. Could be reaching about 100 times compared to FDDT. There is a beam propagation method solver as well as a fiber solver where you design your fibers in single mode, multi-mode, any structure you like. And then the grating software, which you can design gratings on fiber or waveguide. You can design short period grating, long period grating, tilted grating, and so on. The third category is the instrumentation software. And the instrumentation software is used to automate the equipment from any vendor in the market. So you don't need to be stuck to the GUI from a specific vendor. You can operate all these equipments in the lab in the single software. You can communicate with it, set up parameters, you can collect data, and then you can process it. This software is also integrated with OptiSystem software, so you can get data and then use it in the software. This is kind of an overview about the company statistics. We are having our software licensed into different industry corporations, into universities, into research and governmental institutions in over than 80 countries. And then you can see how many citations as well evaluation downloads of the software. This is a snapshot of the companies and some of the academia and institutions. Okay, so now just to show you here how you can download any of the software packages from Optiwave website. What you need to to website and then click on the download. You will have the registration page, and then after you register, you need to use your company's or university email address. And then after that, once you register, you should be able to download any software package on the program files under the C drive, Optiwave software. Then you can have like the software packages once it's downloaded in this kind of representation. Then you have the directories for the drivers, for the files here. As you can see, one important folder is the documentation where you can see important information about the user define how to user manuals, some of the tutorials. One important document here is the release note, which tells you what is implemented in this release in terms of new components, development, improvements, bug resolving, and examples added up. Okay, in this part here, we show you how to can access any video recorded through the webinars or through any special videos added to describe components or describe functionality of the software. You can access it through Optiwave high definition channel on the YouTube, or you can access some of this material through their website, and then the knowledge base where you can have description of like white papers on reproduction of references used for validation of the models used in the software. So this is very good resources. You can refer to it whenever you have any doubt about anything related to the software or you want to learn about the software. Okay, now just quickly here, what I'm going to show you, quickly clicking on through the components we have in OptiSystem, over than 625 components to address everything you need for your designing in different applications. Like, I mean, you have, as you can see here, we have new components as well as you have every time we add up new components to the release to address the needs of the market. These components, you can access them actually if you go to OptiSystem software GUI. If you click onto the GUI and you launch it, you can go to the default. All of these components are categorized in these folders. You can search for any component through the find component and you enter it. You can, if you don't, if you need any component, you can find it this way, and then you can access these components, which is important to build your system. This component can be operation in the bidirectional or unidirectional, so you can transmit signals from east-west or west to east, and also can support single polarization and dual polarization. There is also an OptiSystem tools. There's two tools. One of them is optimization tools, and the other one is the machine learning tool. In the optimization, once you design your system in OptiSystem, you can do single parameter optimization, or you can do multi-parameter optimization. And also you can do, if you have amplifiers, for example, you can design gain flattening filters. And then also you can do the Monte Carlo yield estimation. So you can run the many sweeps of your designs and then create some kind of statistics on the yield and performance metrics. Now, you can access the optimization through the tools optimization, or you can access the optimization setup tool here through the, once you click on the calculate function, you can access the calculator from the GUI toolbar or from the file under file. Once you click on it, you can go to the optimization, and then you can access this window, which give you access to how to set up the parameters of any of these optimization processes. Now, once you want to calculate, you need to click activate this run all optimization, and then run the project from the arrow in here. Now, the other part is the machine learning tool, and the machine learning tool, we did develop this tool to do eye diagram 2 levels training using LNet algorithm, where you could train the system with different parameters through eye diagram. But now in this release, we added up algorithms like linear regression algorithm, and then other algorithms like SVR, linear or polynomial or RBF algorithm. So you can do single parameter or multi-parameter training of your system. Now, in terms of applications, OptiSystem can support many applications. Here, I'm going to list a few of those. One of them is advanced modulation. As you can see in the example library of OptiSystem, we have over than 1,000 examples, which are categorized based on applications. And in the advanced modulation folder, you have subfolders which addresses, like, for example, QAM or pulse amplitude modulation or phase shift keying, probabilistic amplitude shaping, any type of coding of orthogonal frequency division multiplexing. So this is a very good resource actually to design your system and learn how to use the components. So whenever you do search within these folders on your application, and you can basically learn how to use these components and build your system. Other application is for 5G and 6G applications for the front haul, where you can build your system, as well as you can do optical amplifiers. You can design any type of amplifiers from scratch, or you have gain blocks, which is like for amplifiers also semiconductor amplifiers, Raman amplifiers, and so on. You can have application for microwave photonics. There is application for sensors. We support OTDR, Phi OTDR for vibration sensing. There is still fiber bragg grating for sensing applications. There is new applications for LiDAR signal processing. For wireless optical communication channel, there is you can investigate Li-Fi systems, visible light communication, free space optics, satellite communication, underwater communication, as well as the new addition, which is an unmanned aerial vehicle component. We can do design transmission from ground to UAV or UAV to UAV, as well as UAV to ground. Other applications are here. Is spatial division multiplexing, so you can design your few modes, multi-mode fiber transmission, or you can do multi-core, single mode, multi-mode transmission. There is application for quantum key distribution, so you can design discrete variable quantum key or continuous variable quantum key distributions. There is single photon detector components. There is photon number resolving detector. There is single photon laser components. So you can, in these components, you can build on your own system for quantum communication. Digital image processing, there is component which can digitize your images. You can transmit the digitized image. You can reconstruct the image, either black and white, gray, or colored images as well. Photonic integrated circuits, there is components to address photonic integrated circuit characterization. This is very important application because when you do your design of the photonic integrated circuit, you need to analyze this component within the system. So you need to add up this component within a system architecture and then simulate the performance of these components. Machine learning, as I mentioned to you, this is something which we added up recently. Just is quickly to show you that we have over 625 components and 1,000 example of OptiSystem. Now, this slide here shows you how to communicate between all other software packages in OptiSystem, which is OptiGrating, OptiBM, OptiSpice, OptiMode, OptiFDD, OptiInstrument with OptiSystem. So you can design within this software, use your design and import it into OptiSystem and use it within OptiSystem. The other capability of OptiSystem is its communication with external software packages like MATLAB, Python, with C++, with Scilab. So these kind of components allows you to write your own code in the different languages, and then basically either you call OptiSystem from the software packages, or you can call the software from OptiSystem. So you can do both communication. And the last thing you can do is also, like for example, design your photonic integrated circuit using a third party here, Lucida EPCAS software. You can design your photonic integrated circuit and then import it into OptiSystem and then do characterization on it. So we have two webinars. You can check them on our YouTube channel for 4-channel DMUX using ring resonators designed using EPCAS. And also there is a 4x4 cross-connect switch as well. Okay, so here quickly, I'm going to go through the process of integrating the other software packages with OptiSystem. So for example, you design your fiber bragg grating using OptiGrating software. And then what you need to do is you need to get the data for transmission and reflection spectra, and then you load them into the file as you see here. And then once you load them, you should be able to use them and as a component within OptiSystem. Another application here is like, for example, you design using OptiBBM is the MMI, multi-mode interference couplers. Like this is 2x2 MMIs, and you can use them, for example, here at applications like, for example, here in this application is phase shift keying application. You can use OptiSpice, like for example, as I mentioned to you, you can design your optoelectronic circuit like laser drivers here. Or like drivers for the photo detector, and then you can build your circuit around it and then analyze it. You can do, for example, using FDDT, you can design your couplers, and then you can use the S parameter matrix into this component we called optical S parameter. And then you build, for example, ring resonators here. We have a component in OptiSystems called Big Waveguide, and this component, it represents an actual waveguide which you design, its dimensions, and also you can drive it optoelectronically. So you can apply electronic circuits to control the refractive index profile within the waveguide. So within this kind of structure, you can build ring resonators for add-drop multiplexers, or you can use it for the demultiplexer or multiplexer applications. Other thing here, like for example, using OptiMode software, you can design multi-core fiber designs, and then you design them. You can create analyze the modes, and then you import the mode field profiles into OptiSystem. And once you load that, you can calculate the crosstalk between each mode in each core and so on. And then can use OptiSystem to after that to do the transmission and adding up the crosstalk into your system. If you are interested, there is an example in OptiSystem showing this whole representation of these references. Here in this example, using OptiInstrument, so we get data from Tektronix equipment network analyzer, and that equipment doesn't have a DSP. So what we do here, we get the data up to the DSP, and then we do the DSP analysis within OptiSystem software, and then do the PR analysis of symbol error rate analysis and so on within OptiSystem. In this part here, it's showing you, for example, how to design your fiber within OptiFiber software, and then you can take the refractive index profile, dispersion profile, effective, any of these parameters, and you can load them into OptiSystem software. And after that, you can do analysis with them, and you can see how this design will behave in terms of the transmission, as well as in terms of, like, for example, any nonlinearities and so on. Okay, in this part here, just to show you quickly how to access the component resources. For example, you can access them through the datasheet. Datasheet of the components is a very good resource. We recommend always users to read the datasheet because it has the parameter listing, the ranges of the parameters. It has also the theory behind its components, as well as you have references used to design this component. This is very good resources. You can access the datasheet of the component through the help button. Once you click on you double click on the component, you get access to the component properties window, and then you click on the help to access the datasheet. You can access also the datasheet through the documentation, as you can see here on the program files, through this component library, and also you can access them through the start. If you go to the start icon on your window application, and then you can have OptiSystem documentation, and you can access the datasheet through the Explorer. This is, as mentioned to you, the release note. So if you look at the release note, it looks like something like this. So you have the hardware requirements to install the software. You have the new components added up. You have the features improvement in the software. You have the documentation changes, like if we vary anything in the data sheets. And here is the bug fixes, which is could be related to any issues in the software coding. And then this part here is the new examples added up to the example library. So always we add examples to allow the users learn how to use the components. So this is kind of general information about OptiSystem in general. And then now we're going to start with OptiSystem 23 new components added up. So in this release, we added up about 10 components. One of them is the UAV component. The other one is we improved the BERT analyzer, which you can send a single sequence of bits randomly, and then you can receive from different path of the signals. And this is very important for application for quantum, because you need to have, when you do the comparison, you need to compare with the same sequence transmitted. So this is one important application. Another thing you can do, for example, back-to-back analysis with the transmission of the system. There is a component here, the Gaussian mode generator. This is to allow you, once you put a CW light with this component, you can get a Gaussian mode, and then you can look into for example, wavefront distortion and everything inside the UAV component, inside also multi-mode fiber as well. There is these two components allow you to do design LiDAR system. You have very flexibility to position your target anywhere in the channel after free space optic or after, for example, fiber or after underwater. And then you can analyze the signal reflected through the algorithm. Depends on the method you use for transmission of the signal. You can use time of flight or phase shift or frequency modulation continuous wave. So it depends on how you design your modulated signal, and then you can do the analysis. This is called digital pre-emphasis component, which Dr. Abdullah helped us a lot in this design as well as the UAV. This is to compensate for any limitations in your transmission system, like for especially with transceivers when you have DACs or analog digital converter or digital to analog converters or any limitations to the fiber. You can improve your system. You can design your a filter to compensate for any limitation. You can design it in analog domain or in the digital domain. So we're going to show you how to use these components in a few minutes. The other three components here, which is generating random signals, depends if it is optical or electrical signal or a binary or memory. The reason for these three components, we add them up, is to allow the user to mimic an actual representation of the devices. Like for example, if you have a laser, your power fluctuation, you can create that inside these components. If there's, for example, pulse generator, you have pulse fluctuation or phase fluctuation or something, you can all capture it with these components. Okay, now we jump into the examples created into OptiSystem 23.0 using these new components. So this is just to show you how is the new N by 1 BERT analyzer. As I mentioned, this is one sequence transmitted, two sequences coming back. One from them is the back-to-back, and the other one is through fiber. So this is passing through the fiber, and this is back-to-back. And you can compare your transmission. You can do the same thing for quantum communication as well, as I mentioned. This example here for LiDAR applications, you can design your, for example, using OptiFDDT, your antenna, phase antenna, and then eventually you can look at your profile of the laser. You can have a mode generator here to model that part, and then eventually you can design your signal transmitted into the target. You can put your channel, you can put any components in the system, and then you analyze the system eventually. So we have, as I mentioned, three algorithms here. The first one is the frequency modulation continuous wave, which is you can have a sawtooth here, you can vary the frequency, and then you transmit the signal, and then you look at the intermediate frequency here, and then eventually the component will give you the estimated range based on the intermediate frequency detected. The other part of it is if you transmit sinusoidal signal here, and then you amplitude modulate it with the laser, and then transmit it through the channel into the target and detect it. You do the detection, and then you can look at the phase shift between the transmitted and received signal. And then one important parameter is the ambiguity range here. We provide it to you, so to guarantee that this target has to be less than this range, or you have to set up your frequencies again properly to be able to detect the range. So this is all of that can be done through the simulation, and then eventually you can get the range of this component. The third scheme here we do with signal analysis is use time of flight. So you send a pulse, you AM modulate it with the light, transmit it to the target, and then detect it, and then use constant fraction discrimination method at the receiver to detect the range, as you can see here. So all of that is available within the new release. The free space optic applications in OptiSystem, we have many components, as you can see here, to address the different applications. The new component we added up here is the UAV component, which it tells you, for example, how to communicate between ground and between a UAV, between UAV and UAV, as well as UAV and the ground. In this component, we have multi-functionality. We support spatial input beam. We look into plane front, wave front, as well as spherical wave front. We consider the weather conditions. You can have any weather conditions from clear sky, rain, snow, fog, and haze as well. There is a lot of functionality there and models sophisticated to address these weather conditions. We support temporal and spatial scintillation algorithms, so you can look into gamma models. That you can look into log normal model for temporal. We address in other components, for example, like Malaga, you can negative exponential as well as, for example, K model. In the spatial scintillation, we allow the user to either use built-in scintillation algorithms like, for example, column graph or another algorithm, or you can load your own spatial scintillation phase mask like through the spatial, for example, light modulators. Also, you can load your own, as I mentioned, load phase mask. We provide a beam propagation evolution, so you can look at your beam either analytically or numerically, and you can see how is the wavefront is changing along the transmission. We provide capture loss for the receiver and also incorporate beam wandering as well as the UAV dynamics. Now, like mind you can use this UAV component as a free space optic channel as well as UAV, which is this is a flexible way to allow you to either use the capability of the UAV channel as free space optic channel, or if you enable some functionalities like the UAV dynamics in this component, then you can use it as a UAV. So what I'm gonna do here is show you also the Gaussian mode transverse component, which if you are connected to the CW light, basically it generates a Gaussian mode. You can control its spot size, you can control its phase. Here, using the spatial visualizer, you look at the 2D display, or you can look at the 3D display, as well as you can look at snapshot of the 3D, which is show you the Gaussian mode. Now, this is quickly here shows you how we calculate the spatial characteristics of the field. So in the field is characterized with the spatial as well as the amplitude of the field. The beam west evolution from initial beam west into the last receiver position can be using this calculation. We define the spot size, which is twice the beam west. Now, if you look at this diagram here, explains to you that the spot size always is twice the beam west. And then we take into account the relay range using this parameter, and then the radius of curvature, which relates to the phase information of the propagated light beam. And then the beam divergence angle, we use it basically to calculate, either depends on the user how you use it for spot size or the beam west calculation. We can use it using either divergence angle, or the user can enter his own beam west dimension, or also we can calculate it ourselves from the beam. So for example, if you have a beam, multi-mode beam comes in, we can estimate the spot size or the beam west from the incoming beam. This is the diagram show you how the beam evolution goes from the initial beam to the final beam, and then how is the propagate, and start with smaller beam here and then expand it. Now, this relationship is nonlinear, which is helps you understand that if you start with a wider beam here, the progress of the beam is going to be slower, which is very important to address the receiver capture diameter or the aperture of the receiver. This is the phase term of the wave front, which take into account, and this is the terms related to amplitude, and the amplitude has the temporal field of the propagated light. Now, once you add up the special effects is going to cause a phase offset to the propagated beam and could be causing the distortion. So for example, if you pass the light through the free space here with the change in the temperature or pressure or the wind, for example, can cause the beam to go from a clear spot size here to a distorted wave front, which could be causing a lot of troubles for the receiver. You need to use, for example, adaptive optics to correct for these wave front distortions. Okay, so in this part here, we're going to show you kind of an example which been designed to condition and scintillation conditions through the channel, and then allow communicate with another with another UAV, then between the UAV and the ground station. So this is the implementation in OptiSystem, where you have different components to represent the different positions of the beam, and some of these components can be set only for weather. So you disable the telescopes in the transmitter side and receiver side, or you can enable, depends on the application. Then we have the mirror, which is representing the gimbal carrying the reflector here in the UAV. You can load your own reflectivity profiles, or you can use the built-in reflectivity characteristics. So now what I'm going to do, I'm going to run a video which recorded by Dr. Abdullah, and show you a few minutes of how to use the UAV channel. Okay, so give me a second here. So this is the UAV. It's about 7-minute video. I'm gonna mute myself and then we can start here.
Welcome to the fourth example in the UAV FSO link modeling. In this particular example, we'll look at a communication between a transmitter ground station to a receiver ground station. And since there is an obstacle maybe between those transmitter receiver ground stations, a UAV-based relay link is needed. And absent of a line of sight communication between transmitter and receiver, we rely on transmitting the signal from the transmitter base station to the UAV, which then relays the signal to a second UAV, which transmits the signal down to the ground base station. And really, the purpose here is to highlight a few of the capabilities of the UAV channel tool in modeling this particular component. Specifically, I would like to highlight the fact that each of those UAVs has a transmitter and receiver telescope on board. As such, for this very first link, 2.5 kilometers, we have here the telescope is present for the transmitter side on the ground, and a receiver telescope is present in the UAV. The UAV then forwards this or redirects this optical signal using mirror structure into the UAV, second UAV. As such, there is no regeneration, as we will mention later on. There's no electrical regeneration here, and simply we have a transmitter telescope on this link. Now, we've disabled the receiver in this particular link as we will be forwarding the signal into this region of turbulence, and we'll have a channel here with both TX and RX disabled, as this will act primarily as a FSO link without any telescopes and transmitter receiver. The reason we need this is because a single UAV channel component can only accommodate a single turbulence region with Z initial turbulence, Z final turbulence. As such, having a component with both TX and RX disabled enables you to concatenate multiple turbulence regions. And finally, at the receiver end of this telescope, we have the transmitter telescope disabled and the receiver telescope enabled. As such, really, the communication between the two UAVs, there's a transmitter in this end and there is a receiver in this end. And the need for this particular configuration is really to enable the accommodation of the turbulence regions. And finally, for the last downlink here, we have between the UAV hovering at 500 meters above the ground, and then we have here a base station in the ground station. For the final link, both transmitter and receiver telescopes are present. So let us now examine the settings for all of these various components in our configuration. So the first link between the ground base station and the telescope, as mentioned earlier, has a range, a line of sight range of 2.5 kilometers. And in this particular configuration, the transmitter is ground, so this is ground TX, and the UAV RX. Furthermore, the telescope is present at the base station and a receiver telescope is present at the UAV. The height of the transmitter is 50 meters above ground level, and the height of the receiver is 500 meters above ground level. And if we further examine the second channel, which is going to be between the UAV and the line of sight FSO link with two regions of turbulence, we can see that this particular point is modeled using a channel with UAV TX and UAV RX at a 3-kilometer range, and the height is 500 meters for both transmitter and receiver. We also have here the beam waist calculation is done based on the incoming mode, as there is already a multi-mode signal generated from the very first 2.5 kilometer channel. It's actually important to emphasize here that this particular UAV has both a receiver telescope and a transmitter telescope for the sole purpose of forwarding the signal in sort of a relay manner into the turbulence region, and then finally into the second UAV. The optical signal inside the UAV from between both receiver and transmitter telescopes is done through a mirror structure, and really the purpose here is to just demonstrate that no regeneration is taking place, and the optical signal is forwarded as is from the receiver telescope to the transmitter telescope on the single UAV. So this forwarded signal then will be transmitted over a region of 3 kilometers with no turbulence. And finally, we have another region of 3 kilometers here with a turbulence region being present at between 0.6 and 0.7 kilometers, for example. And it's worth noting that in this configuration, both transmitter and receiver telescopes are disabled, as we mentioned earlier, as the sole purpose really is to forward the signal and accommodate a single region of turbulence. And finally, since we have a second region of turbulence, we have here a channel to model the light propagation from this region into the second UAV. As such, a receiver telescope must be enabled here. And we can see now that the RX telescope is enabled and the disabling of the TX telescope is present. And this is indeed the case, and the height is maintained at 500 meters. And the UAV role here is set to UAV TX and RX, as really this is just a sort of a indication of what this link really entails. It's from the UAV TX to UAV RX. However, the role of UAV is inconsequential in these channels, as the jitter, the UAV jitter, is not turned on. Finally, for the final link between the UAV transmitter telescope and the receiver telescope on the ground, we have here this configuration here, UAV TX to RX on the ground. And we also have the heights reversed. So the transmitter height is 500 meters and the receiver height is 50 meters. And if we run this simulation, we're able to see, interestingly, the mode expand, original Gaussian mode from the very first component. And this expanded mode now can be shown here in the receiver telescope of the first UAV. And it's an expand Gaussian mode. And after going through two regions of turbulence, we can see the spatial mode at the receiver telescope of the second UAV, which is distorted. And since the final path, 2.5 kilometers, is also from the UAV TX to ground RX, and we can see the mode here expanded, the distorted mode expanded such. And the same power budget calculation is enabled for all of them, and you can see that there is about 32 dB loss throughout this relay link. On a final note here, you may have noticed in this example that we have intentionally disabled the geometric loss. And this is due to the fact that the geometric loss is determined by a variety of parameters, including the receiver aperture diameter, transmitter aperture diameter, and the beam waist, which dictates divergence angle and your range. Within the parameters in this example, which we had a receiver aperture diameter of 10 centimeters, transmitter aperture diameter of 5 centimeters, and 50 millimeter beam waist with a very small divergence angle. And since the range was maximum 3 kilometers, this actually results in a gain. So we've intentionally omitted the effect of geometric loss. However, if you do decide to enable geometric loss, you will notice that the component will display the following warning below, where it will inform you that the geometric loss actually results in a gain and will be capped at unity, 0 dB, to be within physical considerations. Thank you very much for your attention.
Okay, so let's move on now to continue the presentation. Now, this video, and there is another 4 videos, can be found actually on the YouTube channel, just to show you how to set up the component and also other examples to demonstrate the operation of the UAV component. Now, there is also a video on the digital pre-emphasis component, which we're going to talk about it in a few seconds here, actually. So the digital pre-emphasis component, as I mentioned to you earlier, this component is supposed to compensate for any limitations in the system of bandwidth of either the electronics like the ADC or the DAC. So you have ADC component on the receiver or DAC on the transmitter, or you have limitation due to the filter on the other component. So this component is supposed to compensate for the characteristics here, just to demonstrate the effect of without a deep pre-emphasis or with the pre-emphasis. There is a video I'm going to run actually right now, also a short video recorded by Dr. Abdullah, and that part will demonstrate for you the whole operation, how to design the filter in analog domain and then digital domain. So I'm going to keep also this video running.
Welcome to the first example for the digital pre-emphasis filter component. In this particular setup, we'll examine the application of the DPE filter in a simple IMDD transmission system. Let us go over the components involved in this simple setup. The main layout indicates that a total bitrate of 224 gigabits per second is utilized with a PAM4 modulation format. As such, we have here 2 bits per symbol. Consequently, the symbol rate or the baud rate is 112 gigabaud per second, typical number for Ethernet transmission with the particular overhead involved in FEC encoding and decoding. As such, this is 200 gigabit per second payload transmission link. We will be relying on direct error counting for determining the total bit error rate after transmission. We're using a BERT test set, producing data that's fed into the PAM pulse generator, generating a 4-level signal that is fed into a Mach-Zehnder modulator. As you can see here, the digital pre-emphasis component is meant to be dormant or disabled for the first run. And the electrical drive into the Mach-Zehnder modulator has an amplifier and a laser driver, followed by a bandwidth limiting Gaussian filter. So this filter will essentially emulate the bandwidth limitations of the connections into the Mach-Zehnder modulator. And we will be disabling this for the first run to demonstrate the performance of the link without any bandwidth limitation. We have a CW laser, Mach-Zehnder modulator, and 100 meters of single mode fiber. This is typical for data center type of distance. We have a PIN photodiode and a low pass filter, followed by clock recovery and PAM decisions, symbol to bit mapping, and then we fed back into the bit array test set. If we run the simulation as it stands, without any bandwidth limitation, we'll see that the performance is adequate. In fact, there is no recorded errors, BR is 0, and the simulation is error-free. This is also apparent from observing the eye diagram. You can see here that there is clear eye openings for all of the 4-level signal. Now, in an effort to emulate bandwidth limitations of the transmitter end, we will essentially enable this bandwidth limiting filter. So this is a bandwidth limiting Gaussian filter with 50 gigahertz cutoff frequency. And you can see here that the filter order is 1. So at the end of the day, this is actually your uncompensated filter response in the context of the digital pre-emphasis. Let us run the simulation now with the inclusion of the bandwidth limiting Gaussian filter into the drive of the Mach-Zehnder modulator. And it can be seen here that we have errors showing up, and the log bit error rate is -3.3, which is just below the FEC threshold of 1 e to the -3. And the errors can also be seen manifested in the eye diagram. The eye diagram is fairly closed due to the severe limitation of the bandwidth due to this bandwidth limiting Gaussian filter. In an effort to essentially compensate for this bandwidth limitation, we can see the parameters is a Gaussian filter with a cutoff frequency of 50 gigahertz and a first order. As such, we import the same parameters into the digital pre-emphasis. So if we now look at digital pre-emphasis filter, we're looking at the uncompensated filter response. It will be Gaussian, matching our bandwidth limiting filter, 50 gigahertz with a order of 1. Our desired filter is intended to be wide enough that it accommodates the actual inherent bandwidth of the modulated signal. In this current configuration, we don't have any pulse shaping involved. As such, we don't have any roll-off factor, and we're using a rectangular type of modulated signals. So just to capture the first lobe of this NRZ signal, 80 gigahertz Gaussian filter will be sufficient bandwidth to really accommodate the actual inherent bandwidth of the signal. And we'll enable now the digital pre-emphasis filter, and we see what differences it make in the performance of our link. And it can be seen right away that you have error-free operation with no errors, and observing the eye diagram, you see now that the eye diagram is fairly open and the ISI has been significantly reduced. This is actually one of the key benefits of the digital pre-emphasis component involved. And if we look at the component view, we have a look at the 2D diagrams, we can see the uncompensated filter response, our desired filter response, and the digital pre-emphasis filter response shown in blue. If we just zoom in on this section here, you start seeing that your digital pre-emphasis is indeed compensating a fair bit of the signal. The depth of the filter is fixed to -100 as evident in the main tab of the DPE filter. We can also examine the performance of this filter under a digital implementation by enabling the DPE Z-domain coefficients with a 12-bit resolution, and we can increase the number of coefficients to, let's say, 512. And you can certainly save the values of these FIR coefficients and load them into a digital filter, or you could also load them into a experimental setup or a DAC driver if you have an FIR implementation prior to it. And you can see here that also you have error-free operation with digital implementation, and your eye diagram is error-free. It's not as good as the analog implementation we did initially, as there is always some effects due to truncation, windowing, and the finite resolution of the taps in the FIR coefficient. And we can certainly observe these coefficients here in the 2D view of the diagram, and you can see now we have the initial parts of FIR coefficients. These FIR coefficients are run at a very high speed, which is the analog speed of the symbol rate. You can certainly set your FIR implementation bandwidth to something that is more realistic, that is conformatory to your DAC resolution. So assuming this is 112 gigabaud per second, then if we want 2 samples per symbol, we will have 224 essentially giga samples per symbol, and that would be sufficient for having 2 samples per symbol in our implementation. And if we run this model here, we'll start now seeing a more sort of reasonable and expected response, where the speed of the digital analog converter that will be implemented after the FIR filter coefficient and within the hardware limitations actually is consistent and reasonable. You can still see here we have error-free operation, and observing the eye diagram, it's fairly open. And if we look at the digital FIR implementation here, we can see we have now our FIR coefficients, and presumably we could have gotten away with lower number of taps, as you can see the tap values are fairly small outside 256 tap coefficients. Thank you very much for your attention.
Okay, so let's now continue the presentation. Okay, let's go here and display. Okay, so now the next section is about the vibration sensor, where we use the PHY-OTDR component. Now, the old implementation of the PHY-OTDR is a standalone, so you don't have control of the launching condition. You cannot use amplifiers, you cannot use fibers in front of it or at the end of the or between different components. You can only use one component. Now, the new design here, as you can see, we added up input ports and output ports here. You can, with this kind of scenario, you can control your launching conditions, you can control the amplification, you can cascade many of those, you can put fiber between them, you can look at fiber nonlinearity conditions. So to have much more flexibility, as you can see here for this design. Now, one of these output ports is used for the visualizer, which is a FIO-TDR interrogator. As you can see here, you can look at the position of the interrogation, as well as you can look at the frequency of interrogation. And the other port here, output port, is used for cascading into another fiber or another pieces of vibration sensor. Now, with this kind of scenario, you can design actually a vibration sensor across a premise or something, or far away. You can locate your fibers and then study and investigate what is the conditions which you need to use and how the performance is going to look like. So this is, for example, if you put a fiber of a 10 kilometer in front of the vibration sensor, and the vibration sensor with 50 meters long in this piece of fiber, for example, you can see where is the vibration location here happening at 20 meters. And the position from the transmitter side is going to be giving you, let's say, 10,000, 20 meters. And also you can look at the vibration frequency. Now, can be calibrated to a human pressuring on the fiber, or any kind of object on the fiber. So that can be your vibration frequency as well, to tell what is the object on the premise. So this kind of application. The other part here is just quickly going through the random number generators. As I mentioned to you, you can add it up to your optical signals or electrical signals or memory binary signals. Once you do, for example, the laser, let's say, set up at 0 dBm, you can randomize the signal here using either Gaussian distribution or uniform distribution or Poisson distribution. And then eventually you can you can create kind of Gaussian spread of the power transmitted from the laser. You can do it for the line width. You can do it for any parameters in principle in OptiSystem, which makes it more realistic to the representation. This part here is to demonstrate the electrical signal. So let's say this is a function generator, produces a signal as square pulses in non-return to zero. And then here you can randomize the amplitude of these pulses and then investigate your system based on this fluctuation. The other part here is the machine learning part. The machine learning part, as I mentioned to you, what you need to do so far is to train your system. So the older version, you build your system, you have to collect a large number of, like, for example, eye diagrams, 2 levels. We added up multi-levels right now. You, for example, collect 1,000 images of the eye for different lengths of the fiber, or any parameter you can want it to train your system. So you can train it on the length of the fiber, on the power, or on combination of these parameters or the conditions of the detector. But these eyes are correlated to the conditions. And then eventually what you do, you select certain percentage of these eye diagrams to do the training. And then another percentage of this eye from the training percentage. Let's say, for example, you choose 70% of the 1,000 for training, so 700 images, and then you choose 20% of these 700 images for validation of the training model. And then the last step is to use the testing of this model using the 300 images. And the choice of these images is random through process, okay? And then you can use, as I mentioned to you at this moment, LNet. We had studied other algorithms like ResNet and other like continuous convolutional neural network algorithms. And we find that this LNet algorithm is the best in terms of the number required images to be trained. Now, the other part here is the single parameter. You can do also training similar to what we did on the eye diagram. You can do training on a result. Like, for example, this result could be a single parameter, let's say Q factor, or could be OSNR, or could be anything. And then you can use either linear regression, or you can use, for example, the support vector regression algorithms. There is 3 algorithms built within the SVR. Is linear or polynomial or RPF. Depends on the algorithm selected. These parameters would be open up or gray, which you don't control. And then eventually you can do the training. You can read about the machine learning algorithm through the user manual, the user reference manual. There is the documentation of the machine learning. This is just quickly to show you how the training process goes. You load your eye eventually once you do the training, and then the system will tell you what is the conditions For example, if you do the training based on the length of the fiber and the Q factor, they will be given to you after the training process once you load an eye diagram arbitrarily. Could be another level of network management. We had investigated the machine learning algorithms, as I mentioned to you, using the LNet and WideResNet and the convolutional neural network in an actual system, which we try to address weather condition transmission through any weather conditions. So in this system, we use two amplifiers, power booster and preamplifier, and then control the gain of them to allow always continuous operation of the system based on the captured eye diagram. And then this is the layout of the system. These are the parameters used in the system. We calculate the attenuation between clear sky, which is like around 0.4 dB per kilometer, to 96.8 dB per kilometer, which is like thick fog system. So, and this is some of this analysis of the FSO link, and then how we looked at the BER and the Q factor. And this is the implementation between the predicted Q factor and the actual Q factor, as well as the BER. This is the analysis for the mean square errors after the training and the validation of the system. And then this work has been published in this paper. If you are interested, just send us an email, and then I can send you the email, the paper, or you can discuss any requirements in it. Now, with OptiSystem, always we try to work with collaborators to either universities and research institutions to validate our models. So we had a project with the University of Ottawa and the National Research Council to validate the UAV models and free space optic transmission. So we did some experiments in the lab for the system, which is about like we did transmission, and we have a special light modulator to control the phase mask, and this is kind of different characteristics of the analysis. And also we did a free space transmission through the light, as well as we do power beaming actually with high power lasers like 15 watts using photonic power converter chips. Now this also we are in process of mounting these things on a UAV to test the transmission of the system. This is the link. This is some weather conditions. We capture wind, we capture temperature, pressure, and so on to characterize the scintillation for temporal analysis. And also, this is kind of the dome from inside. This is this part here is the UAV we used for system. This is the mirror, and this is the gimbal. We are trying to calibrate right now the system. And there is some trial already. We did fly it and capture data. We did transmission on it. As I mentioned, there is more data to come in the next couple of months. This project is a 3-year project in collaboration with the different institutions as well. This is the mirror, which is placed at the building with a reflector. This is a mirror that has a enclosure on quality with power supply using solar energy, and this is the mirror actually the communication. So with this, I conclude the webinar and then open up for questions. Please don't hesitate to contact us on the support email or my email here if you have any question or you need a specific application you want to discuss it with us. Thank you very much for listening, and then we're going to go shortly for questions here. Okay, so we have the first question here, Dr. Abdullah. I think it's for you. It's for the turbulence modeling with phase screen. I'm not sure if you see the questions.
Yeah, so the question is about turbulence modeling with phase screens and asking about what's the practical distance for propagation, and also about the adaptive numerical approach. So in the component, if you run the UAV component as an FSO channel or with both transmitter and receiver telescopes, you must account for the expansion of the beam. Now, typically for the applications at hand with UAV, if your initial beam waist is in the centimeter or millimeter range, you can propagate numerically up to 10 kilometers comfortably if you have a sufficient numerical window. Now, you can certainly increase your numerical window significantly to propagate longer distances, but you must account for how much RAM or hardware usage you'll have when you're running the software. Now, if you run the adaptive algorithm, you roughly can get 3 to 4 times more distance. However, you must bear in mind that with this adaptive approach, you're using bilinear interpolation to essentially regrid once the beam gets within margin of the numerical window. And you can control this margin in the tool itself. However, as a user for the UAV component, I would strongly advise to do the calculation before about what the beam expansion should be and account for that when you're running the numerical simulations.
Okay, thank you. There is another question here about also the UAV. Can the UAV component simulate satellite communication links?
So, yeah, so the answer to this question is yes. You can currently use the UAV component in OptiSystem 23 to run satellite links. However, there's a few things you have to watch out for, particularly in the main tab for the UAV component, the attenuation is meant in dBs per kilometer. And when you have a satellite transmission, the slanted range is usually quite large, so 500 kilometers. However, the attenuation is only manifest within the first 20 kilometers of the atmosphere. As such, to circumvent this issue or to go around it, is advised to set the attenuation to 0 dBs per kilometer and calculate what the attenuation is going to be as a lump sum for the transmission and use that and additional losses to kind of emulate this part. And I've also learned that there's an ongoing efforts to create a dedicated satellite communication component OptiSystem.
Yeah, that's true. And hopefully we can release this new component for satellite communication, addressing all of these issues by end of March. Okay, so thank you very much. Now, the question here, can we use the PHY-OTDR for temperature sensor? So it's actually the answer is this PHY-OTDR is used for vibration sensing. And to use for temperature, we have other component, like we have an FPG component or tilted component you can use for also, you can use distributed Raman scattering in our fiber components to be doing temperature sensing as well. Okay, next question is how accurate is the vibration sensor model? Okay, sensor model. This there was experimental validation of the models, and we have data, measured data in the example library, which once you use it within the component, you can validate the model and make sure that it is correct. Is actually it matches the experiment very well. What is the purpose of the LiDAR component? Actually, the LiDAR component is a signal processing component. So it depends on your scheme for transmission of the signal to the target. You can use it for analyzing either as I mentioned, time of flight or frequency modulation, continuous wave, or for phase shift algorithm. I'm gonna go here. This question: can we use the UAV component for free space optic channel modeling, Dr. Abdullah?
Yes, I think the answer is yes. And as we saw in today's webinar, you can actually turn off and on the telescopes and use it just as a propagation channel, right, for free space optics. So it's correct.
Okay. Thank you. And then can we use the machine learning tool for training external collected data? At this moment, with the release 23.0, the machine learning tool can only use data which is generated by OptiSystem within the example you built. So you need to build the example and then generate the data and then launch the tool. But what's happening in the next release, which is 23.1, which we expect by end of March, is to allow the user to load external data into the OptiSystem software. Is actually what we did is we added up a new window into OptiSystem, which allows to script Python script the project, and then you can add up to it your machine learning data algorithms independently. Okay, so next question is, my computer shut down OptiSystem project while calculation to collect the data for training using machine learning. What is the solution? Okay, so again, this is just the same like previous question is we allowing in the future to load the data externally so you can calculate the project in different steps and then could concatenate your results in a single file and then load it into OptiSystem. So this is would overcome issues with RAM as well as your calculation in the project and crashing. Now, I have a question here. Is it when we analyze the BR, the value of BR must be as low as it can, and if it is zero, it is not practical. Please advise. So maybe Dr. Abdullah can answer this question.
Yeah. So,
I
so
mean,
basically, in OptiSystem, there's a variety of ways to calculate the bit error rate, and you must be cognizant of them. If you're using direct error counting, you will get zero because it's going to be error free. And as we saw in today's webinar, there was an example with the digital preemphasis where we had sort of zero errors, and this was with direct error counting. If you want to run direct error counting, if your bit error rate that you're trying to simulate is within 10 to -3 to -4, it's actually a very good way to do it. If you have sufficient noise in your system and you can get some really close experimental results. However, if you're running sort of short pulses or patterns, you can use the semi-analytical approaches that embed error rate calculations. Like, for example, there is sort of a Gaussian approximation or a chi-square approximation, and those are actually exist in OptiSystem that you can run, and they usually give you sort of an estimate of what error rate is, and it could go down to 10 -9, 10 -8. Now, obviously, it's impossible to simulate that number with a Monte Carlo type of direct error counting. So it's used as a semi-analytical way. So again, if you're working in research and development and you submitting sort of work with 10 to -40, you must be aware that this is indeed impractical because simulation tools generally, and even in experimental tools, you cannot wait long enough to measure an error. So as such, you have to be careful of what you present in your results, and the question is valid in this sense. But OptiSystems gives you both opportunities with direct error counting and with semi-analytical approaches.
Yeah. Perfect. Thank you very much, Dr. Abdullah. So I think is right now we are 10 minutes or 5 minutes behind the schedule. So we'll conclude here. And then thank you very much, everyone, for listening. We will be posting the video on our YouTube channel in a couple of days. Thank you very much and see you in another webinar. Bye-bye.
Thank you.